just to recall, we are interested in sequential decision making problems, and and these problems are like this. So basically we are given some initial state x0, and then we go to x1, x2 and so on, and at the kth step we are at xk, and we look for optimal control or action or decision, and this has some cost, and this leads us to xk plus 1. So this is the stage k problem, and then we explore further in future stages until we arrive at the end, which is the terminal state. So we are right now into finite horizon problem. This means that n is finite, and we have defined these things in the last class. We have state denoted by xk and control denoted by uk, and a system is deterministic if states xk plus 1 is generated, is determined solely by xk and uk. So there is no kind of randomness in obtaining xk given xk and uk. So xk plus 1 is obtained from xk uk and via some function fk. Now fk is the policy or the strategy that you will assume to go to the next state xk plus 1. So here k is the time index, xk is the state of the system, uk is the control, and fk describes the mechanism by which state is updated from k to k plus 1, and n is the horizon. So we recall all this, right? And it's good to kind of always keep in mind there are quite a few problems that we are that we have in mind. Traffic light control system could be one example. What could be the state here? The state could be the current traffic situation. So you are building a control system, meaning these lights when they should turn green or red, and it should be kind of dynamic, not fixed. So the current state could be the number of cars waiting at each lane, the current phase of the traffic light. So what is the status? Is red, green, yellow, and the control or the actions could be whether we should switch to green for some specific lane, or whether we should extend the duration of the green light, and outcome could be let's say reduced waiting time for cars or improved traffic throughput. So we may apply sequential decision making in these problems. In self-driving car, we can have the state, which is the current environment and the car conditions, which could be rather complicated in this case. So position, speed, acceleration of the car, nearby vehicles, pedestrians, traffic signals, road conditions, and weather. So state could be a fairly complex in this case, right? Control actions, so the commands to control the car will be the possible control and actions, so which could be like accelerate, decelerate, and then turn, stop, change lanes, or follow specific route. So, and the outcome obviously is safe and efficient driving, and reach the prescribed destination, avoiding collisions and obeying traffic rules, right? So then we have seen inventory level inventory problems already. So here the state is number of units of products available in stock, current demand rate for a product. Actions could be order more units or adjust the production rate, and the outcome or reward or cost, whatever you want to call it. So this would be like avoid stockouts or avoid overstocking as well. Home heating system could be another case of sequential decision making. So here what would be the state? Here will be the current temperature in the house. So it can be measured by some sensors like thermostat. Controls is easy, like adjust the heating, so whether to turn on the heater or when to turn off. Outcomes are comfortable indoor temperature. Robot arm manipulation is, again, you can figure out state, action, rewards. So robot arm could be in certain position or the orientation depending on the kind of robot you have. So angle of joints or position of the and effector, in this case is the robot, these two fingers. Control and actions that you are supposed to take is in this case, let's say you may move some angles, apply specific torques, or move the arm to grasp an object. and outcomes could be successful task execution. In this case, could be pick and place object. We can apply sequential decision making in recommendation system as well. In this case, the state will be user browsing and purchase history, which could be encoded as the items the user has viewed, items purchased, time spent on pages. Control in this case is obviously to recommend, so show specific products or apply discounts. Outcome could be increased sales and user satisfaction. So there are a wide variety of problems. We can go on, and we have not touched the games. So games are pretty much sequential decision making problem. Most of the games are like that. And solving a problem in sequential decision making is about identifying the state, control, and the reward. So once you have that, the formulations that we will have in this course will help you solve a variety of problems. So let us recall again quickly what was the DP algorithm. So the DP algorithm involves two stages. One is cost calculations. So this, as we have seen in the course, that we understand life going backwards. So cost, the way we understand, is like doing these backward computations. So as you can see here, we start with the terminal cost, and then we go backwards. Although the for loop is not written in a backward way, but it's understood that you may go to n-1, then n-2, and so on. So basically, you solve these tail sub-problems. So minimize over the controls of these costs going backward. And then the optimal cost or the final cost is J0, which is where we start from the backwards from n and we end at j. But this is the accumulated cost. So J0 will be accumulated cost starting from n to 0. So this is all the cost, right? J0. So this is our final cost, total final, or I mean the total cost going from 0 to n. So what does this step do for us? This step computes the cost for us, right? So this cost Jn I know, and then minimizing this gives me Jk star for all k, and finally I have J0. So I from this I know J0, J1, J2 up to Jn. Okay, so we have this cost in hand. Okay, and once we have this cost estimates in hand, the next step in the DP algorithm is to then find the, based on this cost, then locate those optimal controls that you will take. So we have seen this. So then the next step is like optimal control sequences, which will require the optimal cost that we computed before. So these optimal sequences, let us say, start from x0. I mean, this is what we do anyway. Start from x0, and then we are looking for what is the best control to go to x1. And this we can find out now because we have the cost calculations there. But this optimization is only over the current set of controls going to x1. Okay, so I'm only looking at x0 to x1. What is the best set of controls I have? So this is minimization only over u0. So u0 is the set of controls from x0 to x1. Okay, I'm not looking at future controls, just the next going to the next one. So this gives me u0 star, which is the optimal control going to the next stage. So this gives us the next state, x1. So we call it x1 star because this is the optimal state that we got to using u0 star that we found from above. So then the remaining steps will be recursive. So at the kth optimal control uk star will be found by looking at the minimum. So in the kth step, I'm looking at what is the optimal control that will take me to k plus 1 step. Okay, so at kth step, I'm looking for the control uk that I'm allowed to take from the set uk, capital UK, which will give me a minimum of these. And J star is already known from the previous cost calculation. So this way we can compute the optimal controls at the kth step for all k. Okay, and once we do that, then we know how to get to the next state, optimal state xk plus 1 star. So what we have understood so far is that the way we understand, way we formulate the sequential decision making problem is we follow two steps. First step is cost computations, which gives us J star, and the second step is finding the optimal control sequence. So these are the two steps. We might play around with this, but this is our first set of algorithm we have. So illustration of DP, and when we do solve these, let's say, these cost computations that we do, then while going backwards, then we get we we solve from the tail. So hence we introduce the concept of tail subproblem. So the very end of the tail is the nth, but then I have n minus 1 to n. So that's the tail subproblem. Then I go higher, then I have n minus 2 up to n. So that's the tail subproblem from starting from n minus 2. So these are tail subproblems, right? So this is how we solve this. In fact, this is how we do the cost calculations, right? In the scheduling problem we saw in the last class, you could see that we scan through the whole subtree starting from, let's say, n minus 2 until the n. Okay, I don't stop at n minus 2 to n minus 1. No, tail subproblem means that if you start from k, then you're going right till the end, n. Okay, so right till the end, which is n. Okay, so so view of tail subproblems is like this. So when I'm looking at tail subproblem, then basically I'm looking at xk, and then the control I can take. In this case, there are 3 possible controls, and this is our tail subproblem. Okay, so in this branch, we may have explored completely so that we and found the optimal cost, which will be j star k plus 1, or we could have found the optimal cost for this branch. Here we are not doing any approximation, so we are saying like we found out the best. If we follow this branch, then we call it jk star xk plus 1 prime, which we get to via uk prime. So we get to xk plus 1 prime via uk prime. If you take another control uk double prime, then we get to another state xk plus 1 double prime, and along that branch there is a lot to explore. So what we are saying here is that that subproblem has the optimal cost jk plus 1 star. Okay, so as you can see, this is not really scalable. Okay, so it's a brute force idea. Basically you will explore all possible branches, all possible cases, and this is not really going to scale, and we have seen this also in the last class. So we have this graph view, which will be used again and again. So basically these problems are like that. We have initial state, terminal state, and then we have possible controls to take, and the stage 1 I can go to multiple states at one, depending on which control I took, and then from here again I can go to multiple states. In this case it's like 2 possibilities depending on which control I took, and then I can have further possibilities. So as you can see from here, these possibilities to explore can really become very big. Okay, so and hence we may need to go away from the classical algorithmic approach to approximation ideas, right? And this is indeed the main thing in this course. So what we will learn is basically approximate dynamic programming. Okay, so in some sense, and more. So all this is now evident here. There is a slightly different view of writing the cost, and it's called sometimes Q factor. I won't use it immediately, but I will just define it and then move on. Okay, and it's really not a big deal. So we are using J, but then some people will write it in terms of Q. So Q factor, sometimes they call it Q values, and axon values, things like that. So there are multiple names of these, and we will see some algorithms later on which will use Q factor. But for the moment, I will only define this. So if I have to define a Q factor, then Q factor is defined like this. So basically, as you can see in Q, we have G added with J star. That's the thing. So basically, it's a neat way to kind of combine both the current cost given by GK, XK, UK, and then the future cost given by JK star. So that's all, okay, for Q factor. So then if we look at J, which is minimization of this, then this could be obtained by minimization of the Q, because this guy is nothing but Q itself, QK star. So J we get by minimizing this, but then we have just defined a new notation for this guy, so we just put in here and we get this. So overall, we can write in terms of Q overall. Okay, so QK plus 1 could also be written in this way, GK XK UK plus minimum of the remaining terms will be GXK plus 1 UK plus 1 plus J star K plus 2 and so on. So all this could be replaced back with Q star K plus 1, which is what is done here. So as I said, as you can say, this is what is the big deal here. You just combine G and then you're calling Q and so on. So it's just a notation. I agree with you. There are quite a few notations in RL literature and dynamic programming literature. So we will, from time to time, we will just highlight these. Okay, so that will be all right now. We will come back to this later on. Okay, so now let us come back to solving some practical problem. So traveling salesman, I define this. This can be really a hard problem to solve in the sense that if I have n cities, then the brute force approach will explore n factorial possibilities, and as you know, n factorial grows really fast. We may go for dynamic programming approach, which is also kind of exponential, so 2 to the n. So as n grows, we know that like if there are 50 cities, then 2 to the 50 is really big number, okay? Given that roughly 2 to the 80 or something is number of atoms in the universe, roughly, right? 10 to the 60, 70, I don't know exactly, but the number of atoms in the universe. So this will be really big. So even dynamic programming approach will be big. So let us recall a little bit about algorithm and why the things that we do is also called as dynamic optimization, like how they are related somehow, right? So if you have done some algorithm course, then how will you solve TSP, right? So what are the ways you can solve? Let us recall that so that we understand why those terms are being used here and how they are related. So let us say I want to solve TSP problem, and here obviously we have represented that graphically. So there are 4 cities, and let us fix one city as a starting city. Let's say 0 is the starting city, and in TSP you will come back and traversing all the cities. That's the problem, and then you have to minimize the cost of travel. The cost of travel is given by the edge weights here. So let us build some intuition for developing a DP algorithm for this. So let us say I fix one trajectory, because I know that there are many ways to traverse this graph, starting from 0 and ending at 0 and going through all the nodes. So one possibility is I follow the trajectory 0, 1, 3, 2, 0. So 0, 1, 3, 2, 0. Okay. So this clockwise thing I want to explore. So this is a possible TSP because I went through all the cities and came back. So that's the TSP problem. Now let us build some intuition behind this. So if I have to come, so the first thing for me is like to have some like cost estimates for this, right? So basically the whole point is to minimize the cost of this tour, right? So in this, if I look at this trajectory, then the cost I will look at is cost from 0 to 1, and then the cost I have from 1 and then ending at 0. So I know that, so this is the total cost where I say now that I am at 1, and 0 doesn't mean like I go directly to 0. Here it means 1 and then traversing the remaining cities and then ending up at 0. So this is what it means. It says now what is the cost going from 1, your current state, and then going through the remaining cities and ending up at 0. So I can write this in this form. I'm trying to kind of relate to what we learned just now in the DP algorithm. It's like g of xk uk plus the remaining cost, right? Okay, so at least for this trajectory. So when the total cost 1, 0 will be called, it will skip 1 obviously because it's already visited. In fact, 0 is also visited. So 0 and 1 are visited cities now. So what is unvisited is now 3 and 2, and then obviously it has to come back. So these it has to keep in mind, and then in this case, according to this trajectory, it will go to 3, and then so in this case again now the cost will be 1 to 3. So going from 1 to 3, and then the total cost going from 3 to 0, ending up at this, and so on. Okay, so this is the way we see this. Now, if I have to write this in this code form, then it could be written as cost from current to next. So that is like g xk uk. So uk is taking me to the xk plus 1. So that's fine. So they have, in this case here, it's like current city to next city cost plus the total cost of the next city until the end. In this case will be the 0, right? So I'm trying to kind of like write this, right, as I'm thinking about algorithm now, right? So, but what we did here is that we just fixed one trajectory and computed the cost. But traveling salesman problem is about what is the best trajectory, okay? So obviously this may not be the best, okay? We have to compute the cost and then see, and we have to do this for all possible trajectories. So then we have to really do other combinations as well, okay? So we have to put that in the algorithm. So we need to loop over all possible trajectories starting from 0, obviously. So also another thing is to remember is to memoize in this case. Okay, so basically it means that if there are sequence of trajectories which were explored before, then those costs should be saved. Okay, you should not like repeat those costs again. So this is a feature of DP if you have seen algo before. So this is so for example, we saw previously, like if I have to compute Fibonacci, then if I have computed so if I have F7 to compute, then F7 is F6 plus F5, and F5 needs F4 plus F3. Okay, and then F6 needs F5 plus F4. Okay, so but then F5 is here, F5 is here. I should not do double computations. If I have computed F5 before, I will save it and use it whenever I need it again. Okay, so it's pretty simple. You know all this if you have done this. So that is called memoize. Basically, in DP problems, you can have overlapping. There's a concept of overlapping substructure or like overlapping computations, let's say, in simple terms. Then you are supposed to not repeat those computations. There can be a lot of overlap in practice, and this is where like dynamic programming actually benefits compared to a purely recursive algo, because you kind of avoid repeated computations, right? So naive recursive algorithm and dynamic programming differs in this major way that you identify substructures and memorize it well. Okay, so now if we look at the when we write it in a recursive way, then it's natural that it will go to the base case. Okay, so your call stacks will be like top-down calls, but then it will go to the base case, and then in this case the base case will be the terminal cost. So terminal cost for this trajectory at least will be 20. So 20 will be 15. So in the call stack it will first compute the terminal 20. So I mean, I should not say like bottom, I should say top, it's because it's a stack. So your top level, your first calls will be right at the bottom, second call above, and then your most recent call will be your terminal cost, which will be 220, so which will be 15. So basically you go backward, right? So it's 15, and then in the stack you have 15 plus what was the cost for this, so 15 plus 30, 45, and then you had this plus what was the cost for this. So this way you compute the whole thing, right? So from 2 to 3 was the cost 3 2 plus total cost 2 to whichever like is visited. So I keep a set where it says which are the nodes already visited. Okay, so that tells me which ones to explore. Okay, so we will see the full algorithm, and then we have 70, and then we have 80 as the final cost. So basically it follows this recursion, which is called again and again on the tails of problem. So right at the tail we have 15 plus 30 plus 25 plus 10. But what is important to view is this recursive thing, right? So so this is what we do, right? So so if we write this in a recursive way, we all know is that it builds this stack, and in the stack at the top level will be your last call. Your last call is this terminal cost at the end of the TSP. Now so this is kind of like a recall of a bit of a DP, and overlapping substructure could be, in this case overlapping problems could be 0 1 2 3 and 0 2 1 3. Both will have the same cost because it's a undirected graph. So either I go from 1 to 2 or 2 to 1. Okay, so you can see 1 to 2, 2 to 1 will give me the same cost, and remaining are the same anyway. So this will be overlapping cost. So this also needs to be figured out in the code, that 0 1 2 3 if I have done before, then if I encounter 0 2 1 3, then I will look at in the table, okay, which was memoized before, was saved before basically. Then I will look up, and that's how I will be n squared to the n, and not kind of n factorial, which will be the real. Okay, so let us look at the complete algorithm, let's say in Python. So I don't think you can really see all this, but overall structure I can point out. Basically it's a recursive code with we have total cost, which is a recursive routine, and then there are some checks whether we have visited all the nodes. So basically visited is a set, and if this visited set length of this visited set becomes n, then we know that all the n cities have been traversed. So in that case it will return, but by then the cost have been computed till the terminal because all the cities have been visited. And then we also do a further check that in the current call, in the current, and then looking at the visited, if it is in the memo. So basically this set of visited, the cost that I'm going to compute now, if it is already saved, because basically it's then we will just return that cost from the saved values. So then it will return, because that's the current job, to give current plus the remaining cost. So then, since it is already saved, it will come out, and then it will be added to the current cost, which is here, right? So this is the main loop. So here we have to explore all the cities basically from the current city. Okay, so from so for next city in the range n, but then whether that next city was visited or not, that we have to check. So it should be not visited. So if it is not visited, then we continue, but we make sure that now that we have visited, we just immediately add that to the visited, because next city we are entering there now. So then but then now next step is to compute the cost. So cost is the recursive form that we derived in the previous example. So cost current next, so going from current to the next, plus recursively call from next onwards. Okay, next onward with the passing with the visited, or technically it's like for the non-visited. Okay, so so from next city to remaining non-visiteds, you go ahead and do the cost computations recursively. So because this is a total cost call, and this is calling the same function here, so hence it's a recursive call, and all this will build a nice stack, inbuilt stack for you. You don't have to like do it explicitly defined stack. This is a function called stack by inbuilt. So it will just work as it is, and then here you will run the problem where the TSP needs a cost table from point A to point B cost, city A to city B cost. So let's say 4 cities, we need 4x4 table of cost, and then we call the TSP routine, and then we set the number of, obviously in this case is 4 number of cities. Memo is initially empty, and visited is 0. We start from 0, so we already put the visited 0, and then let it explore other cities, and then we call this total cost thing. So it will do this recursive call 0, 0 to 1, and then the remaining call will be recursively called, and so on, and all the cities will be explored because of this loop here. So I hope all of you kind of some of you might be very good with these things already, with the DP and all this. So, and those who are not, you may have a look at this algo, maybe run this code and see for yourself how whether you understand all this thing. So the idea here is that the key here is this guy. This is how we see these recursive calls being done. Now let us go back to our view, which is the state control graph, the starting and terminal, and so on. So for the 4 cities itself, and this view will be useful for us for some time, because when we go for DP, but then we will go for approximate DP, look ahead, rollouts. These are the ideas we will explore today. So let us build this graph for our purpose, because so it is the same problem basically. Is the cities are now A, B, C, D rather than 0, 1, 2, 3, and then here we have kind of written down the possible branches that we may explore. So so starting city is A, and then from A we can go to 3 possible cities, so which could be B, C, D. So the next state is denoted as this string AB. So this means that I came from A and I'm at B, and then we have AC. So it's like I started from A and I'm at C, and so on. Okay, so you get the idea, right? And then if we go further on from AB, so basically from the city B, then we have possibilities, because A and B are already visited. So now we have possibilities of C and D. So then we can have 2 possibilities, C and D, and then from here we can once we have ABC, then we can go to ABD. So all cities are explored, and finally we will come back to A. Similarly, this guy, we have ABD, then we can only explore C, and after that we come back to A, and so on for the other possibilities. So basically we have all the possibilities listed here. All possible controls at each stage is explicitly mentioned here. So for our purpose, this graph is more interesting. And this, in this case, the cost matrix is this. Okay, so obviously you don't go from one city to itself, so self loops and all these are not allowed. So this diagonal is like not there. Okay, so So as I said, the brute force approach is possible. In this case, like you can just stare and kind of do you compute the cost for each of these branches, and then you say, look, I found this as the optimal. But the real challenge is when it grows to many cities. Okay, and that's where we need to go for heuristics and approximate DP. Okay, so talking about approximation, so we know that we need approximation, and then how are we going to approximate, right? What are the good approximation schemes? Well, let us develop the maths first, and then we will go back to the practical ideas. So approximation will be basically we replace J star, which is the optimal, by J tilde. Okay, so it's like a usual trend to use tilde when you have approximations. Okay, in the notation here. So wherever we had JK star, we will replace it by approximate cost, which is JK tilde. So as such, it's pretty simple to write, where everything is the same except that J1 star is replaced by J1 tilde, and the control is also a approximate one. In this case will be U0 tilde. So then we get to x1 tilde, which is now not x1 star. So x1 star was our optimal state, but now we are in approximate or suboptimal state. And then we can write down the kth step. So basically you can see J star everywhere is replaced by J tilde, xk star is replaced by xk tilde, and so on. And finally what we obtain is uk tilde, which is the suboptimal control, suboptimal state, xk tilde, and suboptimal cost, which is jk plus 1 tilde. Okay, so but we hope that this is feasible. These approximations are fast, and they can give us some realistic realistic like or like quick solutions which may not be optimal. Okay, so that's what is the case with real life. Real life problems are really hard. You cannot just wait and think I will do the best optimal thing possible. Okay, it's really sometimes not possible. So so remarks on approximation in the value space. The suboptimal sequence, which are the u tilde, u1 tilde, un minus 1 tilde, all this is obtained by going forward. Now this is interesting. What we are claiming here is that in the approximate DP, I may compute this suboptimal sequence while I'm going forward itself. It's like I don't want to go through, let us say, the two-stage process where I did the optimal cost computations first, and then I came to the optimal control sequences as a second step. Okay, so if I'm doing approximation, there may be possibility that I will do it, find this optimal on the fly. Okay, so I can find this on the fly, online basically. So basically when I'm already searching for the best, I will right there I will calculate by some approximations what could be the best control to take, and may not be the best, as I said, this is approximation. So so we are kind of looking at reasonably good control to take. So so in the approximate scheme, it is possible. We will see some practical examples on that. So in this case, no backward calculation is needed, and so why should we do approximation of value space? So I have told you, like even in the TSP, number of cities are 50, then it's like really not feasible. Okay, so the idea is clear for feasibility, reduced computation, and so on. And as I said, it is kind of like selecting the controls in an online way. Okay, so so minimization above, not for every state. So that's the part of the approximation. So the minimization that we are doing is not really for all possible state, because if you do it, then it will go back to the exact DP case. But we will avoid doing that. Okay. So far it's very high level. Like you may say, okay, you're saying about approximations, but then how, right? How are these approximations calculated? Okay. So we will see that step by step. So what are the ways of approximation? Okay, one possibility is something called look ahead. So I may say one step look ahead or two step look ahead. So it's like a thief going to rob a house, and then the thief might do some initial look ahead. So go and see if someone is there inside. Okay, get an estimate. That is a rough estimate. It's a look ahead. Now the person may do a very quick glance. Oh, no one is there, and he can take the next set of actions to go to the house door. No one is near the door. Maybe there is no dog there, or whatever, right? So that initial look ahead could be done by the thief, and then once this is there, and this look ahead obviously can happen in multiple steps. The first look ahead will be whether the outside gate is open or not. Okay, so that's open. So the thief will enter. So this is happening. This is happening on the fly. Okay, so and then go towards the door and then do another look ahead. Look around the house, see if no one is there. Someone may be there, but in some initial look ahead, you're just getting some estimate. Okay, no one, someone is there, not there, and then if not there, you take the next move. Okay, and sometimes you see this in army as well. Few soldiers will kind of go and scan the area. Yeah, so this will be the look ahead. Okay, so they will scan the area, say, okay, it's kind of okay to move in this direction, and then the decision will be taken to kind of really move in that direction. So this is the idea of look ahead. So of course, look ahead could be very complex. I can do one step look ahead, or I can do multiple step look ahead. Like I'm really doing a lot of examinations of the place where, inspecting the place where I need to operate, or I do a very lightweight kind of inspection. So this is the idea here. Okay, since we have the stepwise thing here, so we say one step or multi-step look ahead. Okay, so so the algorithm that we had, which is the approximate DP. So basically, we have J star replaced by JK tilde, which is the approximate cost, and hence the approximate suboptimal states and suboptimal control. So at state K, you look ahead to various possible states xk plus 1. Okay, so as I said, you cannot really be very comprehensive with the look ahead. Like then it will be very costly. So it's like same thing as doing exact DP. So you don't want to do that, obviously. So then you will look at some possible states, and then one step minimization is obtained by minimizing over the controls UK, and then you need to know the approximate cost JK tilde. Okay, so the first step here is like I need to do the look ahead. That was like clear. Okay, I need to do the look ahead, but I still need some estimate after that. Okay, so that estimate is J tilde, right? So what could be that possible estimate? Right, I did a look ahead for one step, but then what would be my estimate for the rest, right? For the total cost, and that will help me decide whether I should proceed or not. So JK tilde is something we need to decide on. So we will come to JK tilde. What would be the estimate, the approximations? Now multi-step, as I said, is like not just looking at the one step, but looking at the L steps. Okay, so basically I am at xk, then I am scanning k plus 1, k plus 2 up to L. Okay, so these many states so all the branches going from k to xk plus L, I will really optimize for this, and from there onwards it will be some tilde estimate. Okay, that need not be from L k plus L onwards. I will leave it on some approximate J tilde, because again you cannot really do throughout till the end, then it becomes exact DP. Okay, so there needs to be a trade-off, right? Okay, so multi-step look ahead typically provides a better performance over the one step, and it seems to be the case, because if I'm optimizing over the one step, or if I'm optimizing over L steps, obviously this L step seems to be better than just doing one step. So if we look into alpha 0,
what we discovered was that actually this exceeded all of our expectations.
Alpha 0 could start in the morning playing completely randomly, and then by tea it would be superhuman level. By dinner it would be the strongest chess entity there's ever been.
After about 8 or 9 hours, it was strong enough to be able to go out and defeat Stockfish, the incumbent world champion, a program which was vastly stronger than Deep Blue, the program which had previously defeated Kasparov.
Which is which is developed for chess by DeepMind. Then indeed multi-step look ahead is essential, because if you play chess, you know that one step, and if you think that, oh, I can kill the pawn, but that is not necessarily a good idea. So in chess you need to think about multiple steps. You may kill the pawn, but maybe your queen can get killed after that. Okay, so so chess is a very good example where long multi-steps look-aheads are needed. Okay. So the intuitive reason is that as the L grows, we expect that j tilde k plus 1, which is the approximate, will become very close to j star k plus L, because obviously if our look-ahead steps are more and more deeper, then obviously I'm becoming more and more optimal. So it's like in chess, if I can think 100 steps ahead, all possible combinations of what the opponent might do, okay, which will be huge, but if I can do that, I'm really very close to exact, right, optimal play. So obviously if L grows, then we get to more and more. But then if L grows, then you need a lot more time to compute these jk tilde. Okay, so this is what I was saying about chess, right? So chess again is a sequential decision making problem, and here there are white pieces, here there are black pieces, and then you need to make a move. So your state could be all possible, your current set of pieces and then where they are. Okay, so usually you write like q, b2 and so on in the and these are the standard things. So that will be your state. Where are your pieces right now? And controls is like what you will do next. So obviously in this case there are multiple pieces. Some pieces may not be able to move because they are constrained, maybe not, but some pieces have freedom to move. So that will be your possible controls, and of course in this case controls are quite interesting, because pawns can move only straight, and then bishop can move diagonally, and the rook can move like horizontally or vertically, and queen can move almost like any step except like a. So multiple possibilities are there, and in this case the one step look ahead will be as if like you make your move, and what are the optimal consequences of that one move, right? So in this case you can think about that. So you have these pieces, let's say white needs to play, then what if you play some of these, right? So let's say you play this queen and you put it here, then this guy rook can kind of kill that. Okay, so you will not play that. So that's where you're looking at like optimal one step thing, right? So in that optimal one step, obviously this putting here is not a good idea because I'm getting killed. And similarly you can play around with this being kept here is also kind of not a good idea, maybe, because the rook can again kill that guy. And then similarly you can think about other things, because there is in chess really there are so many possibilities. I'm not going to go into all those details right now. For example, what if you put this here and then this gets killed by this guy, right? So so these are the one step thing that you may be planning at, right? So which moves to take, and what is your immediate gain out of that. Okay, so the immediate gain is not, I mean, if you look here, then I don't see, yeah, there is one possibility, maybe like the immediate gain if you are just looking at one step, and your reward is like if you kill something, then you get a nice momentary reward, let's say. So in that case, this is the white piece, and then this you can kill this one. Okay, so in the one step you may think that okay, this is the best move I'm going to take. Okay, but this may not be the best move. Okay, so you will immediately get killed by this guy in the next step. Okay, so in chess, one step and winning just in the one step is not a good idea. Okay, so one step look ahead is not a good idea in chess. We all know, basically we all know this, right? So you may plan two step look ahead. So then you may explore. You can say, okay, I'm thinking about two steps. So I'm thinking about what I will do now, and then I will do next again. It's like two moves I'm thinking now. Then let us say I have a queen here, I will put it here, and then in the next step kind of I will plan to kill. Okay, obviously there are consequences that you might get killed as well. Okay, but now you're looking at two steps, let's say, or maybe my plan is to kind of move this here, and then in the next step I will attack the queen here. Okay, but then if you move here, then obviously this might can can create an issue for you. So anyhow, like this is these are the like the two-step plan where you are thinking about two moves. So so in general, if you are a good player, then you will be thinking about a lot more sequence of moves. So definitely not one move. Even a beginner doesn't do only one step look ahead. So so depending on the maturity, you kind of can simulate this in your head, like what are the possibilities you have. So multi-step look ahead for certain problems is really a necessity. So look ahead is one thing, right? So look ahead is like what I will do next. But then what is my intuitive cost estimate? Like I will take that plan. I took one step look ahead, two step look ahead. I do that. That's right. But intuitively, you are planning about some end result. Okay, or you have some estimate of your end result, which is J tilde we are looking for. So do you have that way to compute, have some estimate of the end result, right? So you are doing certain things now, and then you have some estimate for the future that I may want to become like this or that. So how do we get this J tilde, right? What is the way we can even start, right? Because intuition is one thing, right? So we think about intuitions, that's fine, and those intuitions are not really like these expressions like J tilde, and I cannot really put numbers on that, right? So but we need to put numbers here, right? So what could be concrete way to do J tilde? And so we will do something called rollout. So now we have two things: look ahead, and then do the rollout. So what does this mean? Look ahead means that you are exploring the best possible move for the immediate future, and then you are rolling out your estimate from there onwards. Okay, so from xk to xk plus 1 is your one step look ahead. You minimize just for this k to k plus 1 step, and then from there onwards your estimate is some form of rollout. Okay, so what is a rollout, right? So let us define rollout. So so in rollouts, which is a value function approximation or the cost estimate, is the construction of suitable go-to functions. So this is the estimate or the approximate that I am supposed to kind of do, right? So approximation can be done in many different ways, giving rise to some principal RL methods. So this itself is nice area to explore. What are the different ways I can do approximations? So it could be kind of this J tilde may be constructed in an offline way. That's one possibility. You have some way to kind of do cost estimates, let's say, not going into too much detail right now. Alternatively, JK may be obtained online with a rollout. So that's one possibility. And so in rollout, the approximate J tilde are obtained when needed by running a heuristic control scheme. Okay, so that's the thing. So how do I obtain a rollout? It will be some heuristic base policy. Okay, so we will make it concrete, like what is that? So the base heuristic is used for a suitably large number of stages. So that's the whole point, right? Because this is approximate DP, these estimates that I calculate will be using some number of states. Okay, I mean it should be using the large number of states, but obviously not all. So it should be applicable to large number of states, but it's an estimate, approximate. So it's like quickly obtained. So that's the idea. But then, as I said, what is your base policy, right? I optimize the best for the near future, and then I have certain heuristic policy from there onwards. Okay, so let us see. So there are several variants of rollouts involving multiple heuristics, approximation the value space, multi-step look ahead. Obviously, stochastic uncertainty will play a role. Now let us get into some concrete idea. So a high-level plan for rollout. So given a state xk at k, this algorithm considers all tail subproblems that start at every possible next state xk plus 1 and solves them suboptimally by using some algorithm, which is the base heuristic. So so when at xk rollout generates online the next states xk plus 1, that corresponds to all uk in uk, and then we use the base heuristic to compute the next set of sequence xk plus 1 to xn, and the controls uk plus 1 to un, such that we have this xt plus 1. It should be k, I guess, right? No, t is there. Okay, so xt plus 1 will be from xt. So basically, there is a way to generate this, and the corresponding cost is given by the heuristic onwards. So this is our this state. the next k plus 1 is obtained via the look ahead, and the remaining onwards I have a heuristic to apply. So then you will say heuristic applied to xk plus 1, okay, and this will be this set of so this cost is obtained via some heuristic from k plus 1 onwards. So rollout then applies the control that minimizes UK, the tail cost. So basically this is our estimate of the cost, where GK, XK, UK is the UK is the one that we obtained from the look ahead, and the remaining HK estimates are the heuristic. Okay.
Online here, does it mean on the fly compute or what is it?
Yeah, we can do on the fly. Yes.
Online.
Yeah, we can do online. Online, like we can. So this base policy that we have, which we call heuristic here. So after xk plus 1, what is that base policy that I will apply? So this policy is something like that keeps generating k plus 2, k plus 3. This is what policy means, right? So this base policy will generate those set of states until the terminal. This base policy should be like cheap, so that online it doesn't take much time, right? So I optimize to go to the xk plus 1, but after that the base policy that gets applied to k plus 1 and then to k plus 2 and so on, this should be cheap to compute. Okay, so a good example of this will be TSP problem itself. So we will employ this algorithm in TSP. We can do using Q factor. I will skip this because it's just a notation thing. So this is the Q factor. We know that we can combine this whole thing as a Q, right? So there's not really a big deal here. So so note that rollout algorithm requires running the base heuristic for a number of times that is bounded by n. Okay, so rollout n is the number of steps in your finite horizon, and small n is the number of controls you're going to explore in the rollout. Okay, so the total explorations that you will do will be n. Okay, so which is kind of much cheaper than the exact DP algorithm. Okay, so if n is small relative to n, it requires computation equals to small multiple of n. Okay, so complexity kind of reduces, but obviously it's an approximate. Okay, so let us see if we can solve. So this is the traveling salesman problem. And let us do this algorithm so that we get a clarity of what is rollout, what is look ahead, and so on. So this is traveling salesman problem in a generic form, like traverse like n cities, and then the cost to go from city C to C prime is GCC, and so on. So let us look into our plan to solve the TSP, right? So there are many heuristic approaches solving TSP, but what we will use as a heuristic is nearest neighbor. So I think you get the hint already by now. What is that heuristic? Heuristic is the nearest neighbor. What is nearest neighbor in a graph? Basically, if I'm at some city, then what is the least edge weight to go to the immediate next city? That's greedy, right? So greedy heuristic will be our base policy. We know that greedy policy is not a good one for TSP, but we will use this because greedy policy is cheap. Okay, so it's easy to because a greedy policy you are only doing one step look ahead and looking at which one is the cheapest. Tell me, I will go there. Okay, go there. It did not really explore. Okay, this is cheapest, but what about the total thing, right? It didn't do that. So greedy is like, okay, just tell me what is good now. I'm greedy, right? So just tell me what is best, cheapest to go now, and then when I'm there, then just tell me what is cheapest to take. So greedy algorithm can be very fast, but suboptimal. So this base policy we are saying will be greedy, which is very cheap to compute. Okay, so let us see how we will employ this. So starting with the initial sequence. So if we employ the base policy from end to end, that gives me one trajectory. So greedy, let us say starting from the starting city and then right till the end, I can get some cost estimate, but that may not be the best one. Okay, then I will do a look ahead and then explore. So I will do one step look ahead and then maybe explore something else, and then the greedy policy from there onwards. Then I will explore more, then greedy policy from there onwards. Okay, so this is the key idea. So let us do the example, and then it will be better here. Okay, so this is the TSP problem that we decided that we saw before, and this is a 4 city A, B, C, D, and we want to go from A and end up at A, and these are the edge weights given by this matrix. Our goal is to find the least possible path from A and coming back to A as a tour. Now our base policy is greedy policy. So greedy policy means choose the cheapest possible option. In this case, is the edge weight, right? So from A, what will your greedy policy do? What is the nearest city to go? So it will say, okay, the nearest is like, if I look at 5, 1 and 20, then 1 is the smallest. So you go to AC. Then, okay, I'm at AC. What is the cheapest to go from here onwards? So I'll say, okay, cheapest is go to D because it's 3 and this is 20. So cheapest is D. Then I'm at ACD, right? So D, so from D, what is the cheapest to go to B? Well, there is only one possibility, which so you will take that. And then from B, you have to return to A. So that will be this. So base policy gives you this. So base heuristic T0 is this. So we have a base policy, and the whole idea is to improve on the base policy, okay, by exploring. And by exploring, you do look ahead, and you do look ahead and base policy after look ahead. Cost computations, is it better? No, then do another look ahead and then base policy. This is still cheaper than exact DP. That's the point, right? So let us see how. So let us say we go to explore, let us say some other trajectory which we call T2. So T2, so in the look ahead, what you do is that you will not necessarily go to the cheapest now because you are in a phase of look ahead. You want to explore other possibilities right now. So you may explore, let's say 5. Okay, you are exploring. So let's say you went to 5. That's one exploration, and then from here you will apply base policy. So let's say you came here. It was not the best according to greedy base policy, but you said no, let me explore something. Okay, so look ahead also would mean explore something. Maybe there is some other interesting thing to find in the house, maybe. Okay, so you will do this look ahead, and so this is one step. So you will look at, let's say 5, and then you know that your cost is higher than the base. Obviously you know that, and then from here you apply base policy. So base policy is cheap to compute, right? So here from here onwards you're not really exploring, right? So I mean here you will just go greedy, right? So from B you go to D or C. So from here if you apply the greedy, then it's 1 is the cheapest. So you take this, and from here what is the cheapest is this, and cheapest is this, so you come back to A. So this becomes T1 becomes your another so the whole thing is a rollout, right? So this becomes your another trajectory, and now you compute the cost of these. So cost of this is 20 plus 1 21 22, and then 5 is 27. And what was the cost for the base policy? 20 plus 4 24 plus 3 27 and 28. So what you got with this exploration is a cheaper route here, and then you can explore more from there onward. So, and then you if you are here, then you will say, okay, now let me do one step look ahead here, and then see explore some other route compared to what I had before. So you will go with the 4 and this one, okay. So and then from here onwards, you will say you will go with the greedy policy. So greedy policy will be 3 plus 1, and so then you will do the total cost computations. 1 plus 3 4 plus 4 8 plus 5 is 13. Okay, so 1 plus 3 4 8 5 13, right? So this becomes your cheapest route. So what we are doing at each step is one step look ahead other than the base policy we are looking at. Other than the base policy, that's the key to keep in mind. Okay. So this was our base policy, best, looking immediate best, but discard this and look at what is the next best. That's the look ahead. Okay, so next best is 5, hence you explored, and then you applied greedy. You also tried this and applied greedy. You could go ahead and keep doing this. From here onwards, here you don't have many options, right? But if there are more branches, then if you were here, you would do what could be the next best from my previous policy. Okay. So then you will explore that and then apply the base policy down, which is greedy, which is very fast to compute. So you will keep doing that, and that's the way you kind of improve or remain like the current best policy. So it's an iterative algorithm, and as you can see, the whole idea is not to really explore everything. So you will do for a couple of steps, and then you will say, okay, I'm happy with this solutions, and I will stop. That may not be the optimal solution. So that's the idea of DP. So imagine there are 50 cities, right? So 50 branches. So you know this grows like so many possibilities and factorial, right? And then basically in that case you really cannot hope to explore this all branches. So you will do you will start with some base policy. So base policy becomes important. Okay, given the problem you have, what could be your base policy, right? And you are basically improving on your base policy. And this base policy is used to do cost calculations from next step onwards. So base policy becomes critical in this approximate DP idea. Okay. So this is one way to kind of improve on the cost of DP for the TSP problem. Yeah.
Do we go for multiple iterations, to find out? I know like choosing the base is one criteria, so that we make sure that we reach the
Yeah. So
optimal, but because we don't know the optimal, because we have to go for multiple iterations.
yes.
So how would we have approach it? I know choosing base policy is one that you pointed out.
Yeah, you must have a base policy
Yeah.
in the first step, and then you improve on that. Now, improve on that. In this case, we did one step look ahead. If you are interested, you might go for two-step look ahead. So you are not looking for the best other than the base right now, but best until the two steps compared to the base policy. So two-step look ahead in this case will be, so let us say in this case we have, so this is like the two-step process. Now you explore all two-step process as the second best steps to do. Okay, so out of these, let us say 1, 3 is there, so then you have 5 plus 4 is there, and then 20 plus 4 is there, right? So the second best in the two-step look ahead will be 5, 4. And then from here onwards, I have to go for the base greedy policy because I cannot really do exhaustive search. This is costly. Okay, so then I have to rely on my base policy to do the further estimate.
That's the assumption that we're taking, that my base policy is optimal.
Yeah, obviously. No, your base policy is not necessarily optimal anyway. So for some problems like greedy, for some problem, sometimes it's optimal. Greedy policy is optimal, we know, for some problems, but some problems it's not. So it depends. So how do you kind of understand this, right? So let's say you want to build a good chess player. Now, how will you improve on the chess player, right? So you may, as a base policy, you may bring someone who is a grandmaster already, and let the grandmaster play. Okay, so that grandmaster is generating the base policy for you. So when he sees states, he takes some actions. So the policy is all about that. When you are in that state, what were you planning to do? What you will do basically. So that will be the base policy of the grandmaster. And then your next step to improve on that will be to do more rollouts. Okay, he did these steps. What if I take some other steps? And did I win after doing? So you explore other steps, and from next step onward, you bring in the GM policy, grandmaster policy, and say, okay, you play from here onwards. Did you win or not? Win, oh, okay. And you win in smaller steps or whatever. Although chess is fairly complicated because there is an opponent, and there is a stochasticity, which we will model here. Very likely we will we will develop chess program as well in this. So it is fairly complicated. We need to go to the stochastic because the opponent, the move the opponent will play has some randomness because the opponent will have 3, 4 possibilities. Let's say optimal out of 3, 4. Which one the opponent will play, there is randomness there. So we have to model that randomness. So in general, for complicated problem, what you expect is basically some expected reward. In the random case, you will only say expected cost, computations, and so on. So the way to understand base policy is for any problem, you bring in someone who is good at that and generate the policy, and you improve on that. Okay, with rollouts. This is the additional step you do, and you you do something as a rollout, and then employ the base policy from next step onwards, and then you keep doing that. Okay, so in case your exploration led to better outcome, then your policy gets updated to this. If you were in that state, then you will not play like the grandmaster did. You will actually play like the other one because you have seen before that it was better move to do. So your policy got updated now. You might keep old policy also, but you will basically usually you will update your policy. So this becomes your improved policy. Okay, but then this improvement was for this step to the next step. From there onward, the grandmaster was playing. So then you will say, no, okay, but after coming to the xk plus 1, now I do look ahead again. What if I have played something else? And then after that, grandmaster plays again. So was there anything more to improve at the next step rather than relying on the grandmaster policy? So you will explore there. In case you do well, then you will update your policy. You will go away from Grandmaster policy and then ask the Grandmaster to play the remaining set of play. So this is a way of continuous improvement of policy. So now the question is base policy. So in realistic way, for given a problem, you will go with some base policy which is good. If you're playing chess, maybe you will start with some grandmaster policy. For any game, you might bring in some expert and then improve your software based on that. And then if the problem is dependent on like whatever applications, if it's traffic signal, then what is the base policy that you will do? Is the base policy good enough that there are 50 cars? Then I will go for the green light. Or was there anything more, because there is like 100 car that side also. So that 100 car waited only let's say 2 minutes, but this 50 car waited like let's say 10 minutes. So what was the good strategy so that in future like the traffic is more streamlined? So your base policy could be based on number or time as a greedy policy, because base policy by the name itself is not going to be exhaustive. It will be some initial clue basically. So you will say, okay, I'm going with the number. So whenever it goes beyond 50, I will give a green signal. And then whenever the other side goes, so regardless of the time. So even if it has to wait only a few seconds, but it became 50, so I will give a green light. This can be your base policy. You will keep applying, but then you will explore and say, no, what if I looked at other possibilities? And was the traffic signaling better in that case? As a global reward, the traffic was streamlined and so on. So depending on the problem, you have to think what is the good base policy. It will come from the expertise. Like I'm not saying I'm an expert of the traffic signaling system, so traffic police might know all these things better. But yes, and then things can get more complicated. Like there could be randomness involved. There could be certain like incoming traffic for some VIP. We know what happens when VIP comes. So all this might be taken into account. So so base policy as such will be a domain dependent. Working on healthcare, transport, sports, whatever area you are working on, it really depends on what will be your good base policy to consider. Okay, so okay, so I think I will stop here because I have a stochastic DP, which is really the next slide. So anyway, I have to repeat if I start now. So okay, then we can stop.